you very much. I'm very happy to be here, and I'm very thankful to the organizers for giving me the opportunity to present my work here. I'm going to talk about algebraic degrees of phylogenetic varieties, and this is a joint work with Martin Rodica. Okay, let me start saying that we will work with an algebraic varieties. Algebraic variety XGT. This is associated to a finite abelian group. For us, this will be Z2, Z3, Z2 times Z2, so very small groups. And T is a tree, a rooted tree. These are some algebraic varieties introduced by Eriksson, Ranestad, Schumfels, and Sullivan. And these are called phylogenetic varieties. More precisely, these are group-based phylogenetic varieties. In fact, these are toric varieties, and I will not present the construction of these varieties because being a toric variety, it implies that their geometry is encoded by their polytopes. So I will switch to polytopes, in fact, and I will talk about the polytopes. Okay. There are two ways of defining a polytope: by giving the vertex description of a polytope, or by giving the hyperplane description of it. I will start by giving the vertex description, but also the hyperplane description, which will appear later. So we have a finite abelian group, T a rooted tree, E is the set of edges of the tree, L is the set of leaves of the tree, and by leaves I mean edges that are adjacent to vertices. Sorry? There's an echo. Ah, sorry. Okay. It's fine? Please go ahead. Yeah? Okay. And by a leaf, I mean an edge which is adjacent to a vertex of degree 1, and we orient the edges of the tree from the root. I will start by giving two definitions. One of them is for a group-based flow, which is a function defined on edges which takes values in the group, such that for any inner vertex of the tree, so for any node, E0 is an incoming edge and E1 up to EK are outgoing edges. We should have that the associated element for E0 has to be the sum of the elements associated for each outgoing edge. Some example will appear soon. And the second one is for a socket. So this is a function defined on the leaves and takes values in the group G. Okay, such that whenever I take the sum of the associated elements for the leaves, I get the neutral element of the group. And here is one example. If I consider the group G to be Z3 and the following tree, we see that E2, E3, E4, and E5 are leaves. We have only one inner vertex, which is this one, of course. And I can make a socket by considering the association. E1 goes in 1, E3 goes in 1, E4 goes in 2, E5 goes in 2. If I take the sum, this is 0 modulo 3. So I get the neutral element for Z3. And of course, I can complete this, association from a socket to a group-based flow by considering, sorry, oops. Okay, by taking E1 to go to 1, I suppose. Okay, good. And why we care about?
Can I ask a quick question?
Yeah, sure.
So you don't need N and S to be the same. Now you're taking N and S to be the same, but that's just S and N.
Yeah.
They are not necessarily the same function. Are they?
No. In fact, if I restrict group-based flow to leaves, I get a socket, and this association is bijective.
Oh, okay.
Yeah. So if I have this association here for a socket, I can immediately identify a group-based flow coming from a socket. You're welcome. Ah, and by the way, a very yes, sir.
So are we assuming that for group-based flow, the root is getting mapped to the identity element of it?
Yes, if you want. In fact, I don't care about the root.
But the outgoing edges from the root have to be summed to zero, right?
I care only about the inner vertices of the tree.
But I guess the question is, does the root count as an inner vertex?
No, no. So the root is not an inner vertex.
So that let us because within the first definition, like E2 can be anything.
E2,
No restriction.
you can,
Sum of the I know that is the definition of the socket.
E2.
Right? But it's not in the definition of the group-based flow. She's extended the socket to the flow.
Exactly. So a group-based flow should satisfy this condition given by the socket. So the sum of the.
Okay, so you can extend socket to a flow, but not the other way.
Mhm. Yeah.
I think she's just
Okay.
taking the socket and extending it to a flow, although
Exactly.
not in the definition, but
Yeah. Okay, we will see immediately more about this. The thing is that the vertices of our polytopes are in one-to-one corresponding to the group-based flows. And there is a nice algorithm given by Mateusz Michałek for finding the vertices of the polytope. And this goes like this. One, you orient the edges of the tree from the root. For each inner vertex, you choose one outgoing edge. Make a bijection from your group to the standard basis of Z to the cardinality of G. And then consider all the possible associations of elements of G with non-chosen edges. Step 5, for each such association, you make a full association. So this means that you complete to a group-based flow, and you output the vertex of the polytope. Let's see this one example. I have a simpler tree. The group is Z2. I have only one inner vertex. As I said, I have to pick first an outgoing edge. I pick E2. You can see here how I mark this. Then I have to consider the standard basis of Z2, epsilon 1, epsilon 2. Yeah. Maybe I should write here that epsilon 1 is 1, 0, and epsilon 2 is 0, 1. I consider this a map from Z2 to my basis, which is epsilon 1 and epsilon 2. And I make all the associations that I can make with the non-chosen edges. The non-chosen edges are E2 and E3. And I can have 0 goes in E1 or E3, or 1, this can go to E1 and E3. I have to fulfill to get a group-based flow such that the sum should be 0 in the group Z2. So here I'm forced to put 0, here I'm forced to put 1, here I'm forced to put 1, here I'm forced to put 0. And now to output the vertices of my polytope, I go back to my bijection B, which is defined 0 goes in epsilon 1 or 1 goes and 1 goes in epsilon 2. So for this 0, I have to write epsilon 1, which is 1, 0. For this 0 again, I have to write 1, 0. For this 0 again, I have to write 1, 0. For this will give me the following vertex. For 1, I will have epsilon 2, which is 0, 1. Then for 0, I have 1, 0. And for 1, I have again 1, 0. So I have 4 vertices living in R6. And as you can see, the tree is very small. So the tree, this tree is called a tripod, a 3-claw tree. Okay, we will see later. For example, if I look at the same tree and I consider the group Z2 times Z2, I will have 16 vertices living in R12. So it grows very much. Okay, so I said at the beginning that we want to compute some algebraic degrees for some toric varieties, but computing these algebraic degrees is in fact the same as computing the volume of the associated polytopes. So our question now is how to compute the volume for such polytopes. One idea is by looking at the Ehrhart polynomial. Ehrhart series is in fact there. And we know that there is a very nice relation between the volume of the polytope and the number of integral points contained in the polytope. We try to compute some Ehrhart polynomials somehow to play with these ideas. We didn't succeed to find something interesting. Okay, another thing is by looking at triangulation into unimodular simplices. This relies to computing Grobner bases. Well, it's bad again. We were not able to compute any nice Grobner bases. And in fact, there is only one paper in this direction where the author said that they offer somehow a Grobner basis computation for any tree of this form. This is called an M-claw tree. So I have only one inner vertex and M edges. And for Z2, they claim that they found the quadratic Grobner basis, but in fact, we found a mistake in their paper. And it works only until M is 6 or 7. So it's bad.
Always has a regular modular triangulation. You consider polytopes, and this polytope always has regular unimodular triangulation. At least unimodular triangulation.
Via the cut polytopes, you mean?
Or you consider this polytope?
Yes, I mean for this polytope. No, I mean at least the Grobner basis that is proposed in that paper doesn't work. Yeah, and there is nothing else known. And we were not able to fix the issue in that paper. Okay, there is some relation also with the cut polytopes in the KZ2. This is why I said, but I'm not going in that direction. Okay, so in conclusion, we don't have a method. Okay, but I promise that we will compute volumes, right? Okay, so first of all, we will restrict to this class of trees. And this class is very important because there is a very, very nice result due to Seth Sullivan saying that if you have, if you look at the polytope for an arbitrary tree, then you can obtain that polytope via some gluing, via some gluing of smaller polytopes associated to this kind of trees. By gluing, there is a very nice process which is called toric fiber product and so on. And this has very nice consequences when looking, for example, at the normality of the polytopes. So, for example, if you show normality for this kind, so for the polytopes associated for this kind of trees, then this will give you normality for arbitrary trees and the same group, of course, so you fix the group. Also, due to this result and another result of Mateusz Michałek, the polytope for an arbitrary tree, it will contain as a face the polytope for this this tree, and in particular for the 3-claw tree, which is this one, the smaller one. So if you have non-normality for this kind of tree, this will spread the non-normality for bigger trees. And we have also some results in this direction. And also the Gorenstein property, this behaves nice. So if you glue the polytopes along the standard simplex, the Gorenstein property behaves very nice via this toric fiber product. Okay, so this class is a very nice class of trees that one can consider. And if we look at the group Z2, so what I will present today, it will be very much related to the group Z2 and Z2 times Z2. We have results for these two groups and these kind of trees. Okay, we have also for Z3, but I'm not going to explaining it today. For Z2 and this kind of tree, our polytope looks like this. So it is a simplex by cutting off 4 unit simplexes from the cube. 3, you can see them, and the 4th one is behind. And this is something that can be generalized, and P, Z2, and N for the N-claw tree, this can be regarded in the interior of the cube by cutting its corners. Okay, but if you want to cut corners, it means that we have to discuss about hyperplanes and facet description. And for Z2, the facet description looks like this. I'm not gonna enter too much in the details, but this is the facet description for Z2, and this is a result due to Buczynska and Wisniewski. And from the facet description, we can take our polytope, visualize our polytope by seeing as the cube minus this union of intersections of the cubed hyperplanes. And we can compute the volume. This is the volume in the lattice Zn. Okay, and we got n factorial minus 2 to n minus 1 times 1. But in fact, what we need in order to get the algebraic degrees is the volume in the lattice generated by the vertices of the polytope, not Zn. And this is the lattice generated by the vertices of the polytope. There is also one example here, but what is of interest for us is the fact that our algebraic degrees will be n factorial divided by 2. So I have to divide everything by 2, which is the index of the sublattice, minus 2 to n minus 2. Okay, so this is the behavior in the case Z2. This is the toy case, let's say. For Z2 times Z2, we try to apply the same strategy. And instead of visualizing the polytope in the interior of the cube, this time it will be in the interior of the product of simplices, delta 3 to n. And we play the same game, but this time things are much more complicated because the parts that we cut off intersect, and we have to compute extra volumes for those intersections and to use some kind of principle of inclusion and exclusion. The facet description is due to Mohar, Rusinsko, and Vernon. And this is our polytope in the case Z2 times Z2. And the final explicit formula is exactly this one that you can see on the board. Yeah. Okay, and again, this is the volume in Z3n, and we want to compute it in the lattice expanded by the vertices, and this means divided by 4. The tree is this one. Yeah, enclosed tree. Okay. And we try to push it further. So for example, for Z2, we try to compute some recursive formula for an arbitrary tree, because the toric fiber product is not that useful when computing the volumes of polytopes. And the formula we got, so for Z2, and here in fact, let us consider F to be a tree. It's more general, it's for a forest. But we have some recursive formula computing the volume also for an arbitrary tree and the group Z2 for these polytopes. Thank you very much.